Welcome back to the Deep Dive podcast, where we explore the cutting edge of artificial intelligence. Today, we're diving into a fascinating paper published at the International Conference on Learning Representations, ICLR, in 2019, titled DARTS, Differentiable Architecture Search. Joining us is Dr. Researcher Name, the lead researcher on this groundbreaking work, and Dr. Field Expert Name, a leading expert in neural architecture search. Welcome, both of you.
Thank you for having me. It's great to be here.
It's a pleasure to be here, too. I'm excited to discuss this paper. So, Dr. Ed Researcher Name, let's start with the basics. Why is architecture search such a crucial problem in deep learning today?
Well, it's all about building the right tools for the job. Imagine you're trying to build a house. You wouldn't use the same tools for laying bricks as you would for painting the walls, right? The same applies to neural networks. The architecture or structure of a network determines its capabilities and how it learns from data.
Exactly. And historically, this design process has been very manual and labor-intensive. It requires expert knowledge and often involves lots of trial and error. That's where automatic architecture search methods come in, right? The goal is to automate the process of finding the best neural network architecture for a specific task, saving researchers time and resources. But as the paper points out, existing architecture search methods have faced a major hurdle: scalability.
That's right. Methods like reinforcement learning and evolutionary algorithms, while successful, are incredibly computationally expensive. It could take thousands of GPU days to find a top-performing architecture. It's not very practical for most research projects.
So, what is the main innovation that DARTS brings to the table?
DARTS takes a fundamentally different approach by making the search space continuous. Instead of searching over a discrete set of candidate architectures, we represent the architecture as a weighted mixture of operations on each edge of the network graph.
So instead of choosing one specific operation, like convolution or pooling for each edge, you allow for a blend of multiple operations. That's quite different from how things were done before.
Precisely. And this continuous relaxation allows us to leverage gradient descent, a powerful and efficient optimization method to search for the best architecture. It's similar to how we optimize the weights within a network, but we're now optimizing the architecture itself.
That's fascinating. So you're essentially using the same machinery that we use for training neural networks to design the networks themselves. That seems very elegant.
It is, and it allows us to find high-performing architectures with orders of magnitude less computational cost than traditional methods.
What are your thoughts on this approach? How does it compare to previous attempts at making architecture search more efficient? It's a very clever idea. Previous attempts at speeding up architecture search have focused on things like imposing structural constraints on the search space or using performance prediction models. But DARTS goes a step further by fundamentally changing the way we search for architectures. It's like we've moved from a discrete, pixelated view of the architecture space to a smooth, continuous landscape, allowing for more efficient optimization. Can you elaborate a bit on the technical details? How does DARTS actually implement this continuous relaxation and gradient-based optimization?
Sure. The core idea is to represent each edge in the network graph as a mixed operation. This mixed operation is a weighted sum of all the candidate operations, with the weights determined by a vector called alpha. We then optimize this alpha vector using gradient descent, which effectively controls the relative contributions of each operation to the final architecture. And this optimization is done by minimizing the validation loss, which is a measure of how well the architecture performs on a held-out set of data. But there's a catch. The validation loss depends not only on the architecture, but also on the weights within the network. So it's not just a simple optimization problem, it's a bi-level optimization problem, where we're optimizing the architecture, alpha, while simultaneously optimizing the network weights, W, for that specific architecture.
That sounds quite complex. How do you handle this nested optimization process?
It's challenging, but DARTS introduces a couple of clever approximations. The first-order approximation assumes that the current weights are close to the optimal weights for the given architecture, and it directly optimizes the validation loss with respect to alpha. The second-order approximation uses a finite difference method to estimate the Hessian matrix, which captures how the gradient of the training loss changes with respect to alpha, allowing for more precise updates to the architecture.
So, the second order approximation takes into account how the weights would change if the architecture changed. That sounds like a more sophisticated approach.
Exactly. It leads to slightly better performance in practice, but it does come with a higher computational cost. The first order approximation, while simpler, can still be quite effective and provides a good balance between accuracy and efficiency.
That's fascinating. So, after the optimization process, how do you actually get a concrete architecture out of this continuous representation?
We use a process called discretization. Essentially, we select the top k strongest operations for each node in the graph based on their learned mixing weights. This gives us a discrete architecture that we can then train and evaluate.
Let's shift gears and talk about the experiments. What tasks did you evaluate DARTS on?
We evaluated DARTS on two key tasks: image classification and language modeling. For image classification, we used the CFAR10 dataset, and for language modeling, we used the Penn Treebank PTB dataset.
And what were the results? Did DARTS live up to its promise of efficiency and performance?
It did. DARTS achieved state-of-the-art results on CFAR10, matching the performance of the best-performing methods like NASNet and AmoebaNet, but with orders of magnitude less computational cost. It also outperformed existing efficient methods like ENS, which use reinforcement learning.
That's impressive. And what about the language modeling task?
On PTB, DARTS discovered a recurrent architecture that outperformed even hand-tuned LSTM models. It achieved a perplexity of 55.7, surpassing the best-tuned LSTM model, 58.3 perplexity, and ENS, 63.1 perplexity, while using similar or lower search cost. These results highlight the power of architecture search in finding architectures that can surpass traditional, handcrafted designs.
So, DARTS is not only efficient, but also effective in discovering architectures that rival or even outperform the best human-designed ones.
That's right. And even more impressive is the fact that DARTS also demonstrated transferability. The architectures learned on CFAR10 and PTB transferred well to ImageNet and Wikitext2 respectively, showing that the learned architectures have a degree of generalizability.
What are your thoughts on the implications of these results? How do you see DARTS impacting the field of neural architecture search? I think it's a game changer. DARTS has shown that gradient-based optimization can be incredibly effective for architecture search. This is a major shift from traditional discrete search methods. It's not just about efficiency, it's about opening up new possibilities for exploring architecture space. We can now design networks with more complex structures and potentially even more powerful capabilities. And the fact that it can find architectures that generalize well to different tasks is incredibly promising. It suggests that we might be moving closer to discovering architectures that are more general purpose and adaptable. That's a very exciting prospect. But of course, no research is without limitations. What are some of the challenges or potential weaknesses of DARTS that you see?
One of the biggest challenges is the gap between the continuous architecture representation and the final discrete architecture. The algorithm optimizes the architecture in a continuous space, but ultimately, we need to choose a discrete architecture. This mismatch could potentially lead to suboptimal performance. And the computational cost of the second-order approximation can still be significant, especially for large and complex networks. This might limit the scalability of the approach to architectures with a large number of parameters or operations.
So it's a trade-off between accuracy and efficiency. It's great to have this powerful tool, but it still needs refinement for even larger scale applications.
Exactly. And there are other challenges as well. For example, the performance of the algorithm is sensitive to hyperparameters, such as the learning rates for weight and architecture optimization. Finding optimal hyperparameter settings can be quite challenging and might require extensive tuning.
So DARTS, despite its remarkable progress, is still an evolving approach. What are some of the key directions for future research?
One direction is to explore techniques that can bridge the gap between the continuous architecture representation and the discrete architecture. For example, we could use annealing techniques to gradually enforce one-hot selection of operations during the optimization process. Another area for exploration is performance-aware architecture derivation schemes. Instead of simply selecting the top K operations, we could incorporate the shared parameters learned during the search process to guide the selection of the final architecture. This could help to ensure that the derived architecture is not only efficient but also performs well.
Those are excellent ideas. And of course, there's always room for improvement in the optimization process itself. We could investigate higher order derivatives or more sophisticated approximations for the architecture gradient to further improve the algorithm's efficiency and accuracy. And beyond those technical details, it's important to apply DARTS to a wider range of tasks and datasets. We can explore its capabilities for things like object detection, reinforcement learning, and even graph neural networks. Do you have any additional thoughts on the future directions for DARTS and the field of architecture search in general? I think it's a very exciting time for architecture search. DARTS has shown that we can move beyond discrete search methods and leverage the power of gradient-based optimization. This opens up a whole new world of possibilities for designing more efficient and powerful neural networks. In the future, I anticipate seeing more research on combining different techniques like gradient-based search with reinforcement learning or evolutionary algorithms to create even more powerful and adaptable approaches. Indeed, it's a very dynamic field with a lot of exciting potential. Doctor, do you have any concluding thoughts on what we've discussed today?
I think DARTS represents a significant step forward in the field of architecture search. By moving towards continuous search spaces and gradient-based optimization, we can explore more complex architectures and discover networks that are both efficient and performant. This opens up a lot of exciting opportunities for future research and applications in deep learning.
Thank you both for this insightful conversation. This paper has definitely given us a lot to think about. Listeners, if you're interested in exploring this research further, you can find the paper and its open source code on the ICLR website and GitHub. We encourage you to dive deeper and learn more about this groundbreaking work in architecture search. And be sure to join us next time for another deep dive into the world of artificial intelligence.